Come on, my dears. Last time we had finished section D. Now we proceed further in chapter number 2. We begin with new section, that is section E for exercise numericals, correct? And in chapter number 1 also we had given symbol EN, that is exercise numerical. Okay? Kindly read the statement of first exercise numerical. Have you read it? Come on. We have 2 point charges. Q1 equals to 2 coulomb and Q2 equals to minus 3 coulomb. Out of which this 2 coulomb point charge is located at origin and another point charge minus 3 coulomb is located at that point which has coordinates 100, 0, that many meter. Now you know if y coordinate is 0, that point must be on x-axis. That's why that point I have chosen here. That point is point P. Okay? And this much distance will give x coordinate of this point, which is 100 meter. So this total distance is 100 meter. Distance OP is 100 meter, correct? Now what we have to find out? We have to find out the coordinates of those points along the line joining these two charges where total electric potential becomes 0. Let us find out. Remember, such a point where total electric potential due to a system of two charges located along same straight line passing through them becomes 0 at that point where which is the position of which is closer to smaller charge and away from bigger charge. I repeat, in case of a system of 2 point charges, remember the position of that point where total electric potential becomes 0 is closer to smaller charge and away from bigger charge. You can find out such two positions in this case. I am showing you. Consider this point, say point A, which is closer to the smaller charge and away from this bigger charge. Take magnitude here, it will be plus 3 compared to plus 3, this plus 2 is smaller. So I am showing this point A closer to the smaller charge and away from bigger charge. Okay? This distance, I don't know, let it be x1, which I have to find out. This total distance OP is 100 meter, out of which this much distance is x1 and remaining will be 100 minus x1, that is 100 minus x1, correct? I repeat, suppose this much distance is x1, then what was this total distance? 100 meter, out of which this much is x1. So naturally remaining must be 100 minus x1, correct? Fine. Now another point B you can choose here, which is also closer to this smaller charge and away from this bigger charge. And that point B has coordinate, x coordinate suppose x2, and because it is a point on x-axis, y coordinate would be 0, correct? This point A is also on x-axis, so its y coordinate is also 0. In short, we have to find out coordinates of points A and B. Okay, fine. Then you may have a question that one point we have selected in between these two charges, one point on the left of this, then why not one point on the right hand side of this charge? No, you will not get any such point on the right hand side of this bigger charge, because if at all you select a point over here, it would be closer to bigger charge and away from smaller charge. No, it is not possible. I told you, a point where total electric potential becomes 0 in this case is closer to smaller charge and away from bigger charge. Okay? If you select point over here, it will not be possible, because otherwise it will be closer to bigger charge and away from smaller charge. Not possible. Okay, fine. Now at point A, total electric potential I am taking by symbol VA, which I want to be 0. Correct? Tell me, as many charges, that many values of electric potential. We have 2 charges, so we should get 2 values of electric potential, and then their algebraic summation we should take 0. Correct? Come on. Potential due to a point charge, it is K into charge upon distance. K into first charge is Q1 divided by distance of point A from first charge, which is x1, plus potential due to second charge, K into second charge divided by distance of point A from second charge. K into second charge is Q2 and distance of point A from second charge is 100 minus x1, 100 minus x1. Correct? Now K and K you can take common, then after you can take it in the denominator of 0, 0 upon K will be 0. Now Q1 is plus 2 coulomb, Q2 is minus 3 coulomb, x1 as it is, 100 minus x1 as it is. Simplify, find out value of x1, it comes out to be 40 meter, 40 meter. Okay, fine. Now what about potential at point B? Similarly, come on, as many charges, that many values of electric potential. So at point B also we will get 2 potential values, one due to this charge, another due to this charge. Come on, you know potential at any point due to a point charge, K into charge upon distance. K into first charge is Q1, but might well now distance of point B from first charge, which is x2. I must write here x2, plus potential at same point B, but now due to second charge. So it is K into second charge, which is Q2 divided by distance of this point from this charge, that is you require distance P to B, P to B, and that distance would be this much distance plus this much distance. Correct? This much was already 100 meter and plus this much, that is x2. So I should make addition of 100 and x2, then 100 plus x2. Correct? Last time, distance of point B from this bigger charge would be this plus this, and this much is 100 meter plus x2. So I am writing 100 plus x2, and that equals to 0. Find out x2 from here, it comes out to be 200 meter. x2 is 200 meter. Okay, fine. But now we should express our final answer by locating the positions of those 2 points. How can you locate any point? How can you find out its position? By its coordinates. So we must specify the coordinates. For point A, which were the coordinates? x1, 0. x1, 0. x1 came out to be 40 meter, 0, that many meter. But now take care while just mentioning the coordinates of point B. Because point B was on negative x-axis, I must write its x coordinate negative. No doubt x2 value comes out to be 200 meter, but that x2 is the distance. Now we are writing coordinate. Coordinate of that point which is on negative x-axis must be negative, so minus 200. Correct? Same value with a negative sign. And for any point on x-axis, what is this y coordinate? 0. Correct? So this is our final answer. Okay. Now read the statement of exercise numerical number 2. Read it? Look. My dears, this example is quite similar to illustrative numerical number 12. It is only a change of symbols, that's all. Mere a change of only symbols, no other change I am showing you. Just recall that problem which we had discussed in the illustrations number 12. We had 2 spheres with radii r1 and r2. Initially, the first sphere had total charge capital Q. and initially second sphere was chargeless, and then after we had connected the surfaces by some metallic wire, that is conducting wire. Then what had happened? There was a flow of electrons from a surface of lower potential to a surface of higher potential. But how long that flow of electrons continued? Till the electric potentials on the surfaces of both the spheres become equal, correct? And then after, in the final condition, what is the amount of electric charge on the surfaces of both the spheres? That is what we had obtained the formula where this way, charge in the final condition on the surface of first sphere was total charge upon total radius, that is how I told you to remember in words, total charge upon total radius multiplied by radius of first sphere, that is R1, correct? Similarly, what was the charge on the surface of second sphere? Q2. It was again total charge upon total radius multiplied by radius of second sphere, correct? Now in this example, there is a change of only symbols. Instead of Q1, we should write QA. It is a charge on the surface of that sphere whose radius is small a, correct? Come on, total charge upon total radius. Total charge is capital Q only, but total radius means summation of radii, two values of radii, that is small a and small b. So small a plus small b. This gives me total of radii of two given spheres, and multiplied by, if you are writing here charge on the surface of sphere A, then you should write here in multiplication radius of sphere A. Radius of sphere A is small a, got it? Similarly, what will be charge on the surface of sphere B? Let it be QB, correct? Then again it is total charge upon total radius multiplied by radius of second sphere, which is small b, correct? Fine. Now you know in the final condition the potentials on the surfaces of both the spheres have become equal. So whatever is the value of VA, same is the value of VB, and this equal common value I am showing by symbol capital V. Come on, VA, what is it? Potential on the surface of sphere A. For a charged sphere, what is the potential on the surface? K into charge upon radius. K into charge upon radius. K into charge on the surface of sphere A, it is QA, divided by radius of sphere A, which is small a, correct? Similarly, what will be VB? It will be K into QB upon small b. Now we are asked to find out this common potential. Let us find out. V as it is, from here K upon A as it is, K upon A as it is, multiplied by QA. What is QA? What is QA? It is Q upon A plus B into A. Q upon A plus B into A, correct? Now this A and this A will cancel, giving you K into Q upon A plus B. K into Q upon A plus B. That is inverse. K into total charge upon total radius. K into total charge upon total radius. Got it? Somebody may find out the same formula using V equals to VB. No problem. Then he will write this formula. Correct? At that time he will write K upon B into QB. But QB is this much. Correct? At that time BB is getting cancelled, and finally you will be getting same result. K into total charge upon total radius. Simple. Please remember this final result, because sometimes they may give you numerical values of these quantities. They may ask you to find out this electric potential in volt. So at that time you will not require to derive this result. If you remembered, you can make direct use of it. Okay. Fine. Read now statement of number 3. Read it? Come on. We have potential formula given in terms of coordinates of point P, say having coordinates x, y, z. Here in this statement they have given all the coordinates to be 1 meter each. X coordinate is also 1 meter, y coordinate is also 1 meter, z coordinate is also 1 meter. Now what is that potential formula in terms of coordinates of point P? I am showing you. They have given like this. 2x square y plus 3y cube z minus 4z raised to 4 into x. Okay. Now we are asked to find out the electric field in a vectorial form at that very point. You know vector A, as you studied in 11th standard, vector A equals to ax I hat plus ay j hat plus az k hat. So in order to express any vector in 3 dimensions in a vector form, you must find out first of all its 3 mutually perpendicular components. That is why we require here the 3 mutually perpendicular components of electric field, that is Ex, Ey, Ez. Let us find out them one by one. First of all, we go for finding Ex. As you have studied in the theoretical part of the chapter, it is minus del V by del X, that is negative value of partial derivative of potential with respect to x. Okay, fine. Minus del by del x as it is of a V, V formula, same formula I am writing here, same formula, no change. Okay. Now this minus as it is, you know whenever you take partial derivative with respect to x, then y and z are to be treated as constants. Remember that? Fine. Use it here. Minus as it is, 2y is right now constant, I am taking it out. Then del by del x of 2x, del by del x of x square, minus and as it is, 2 into y is constant. Now del by del x of x square, del by del x of x square, that is derivative of x square with respect to x, it is nothing but 2x, power you should write as a multiplier into x raised to 2 minus 1, 1 power less you have to write, correct, 2 minus 1 that is 1, x raised to 1 that is x, simple. Now minus plus minus, but when I am taking partial derivative with respect to x, then y and z are to be treated as constants. So this is altogether a single constant term, and derivative of a single constant term is always 0, correct. Now minus minus plus, 4 into z raised to 4 is constant, derivative of x with respect to x is 1, correct. Fine. Now this is minus as it is, 2 to the 4 into x into y plus 4 into z raised to 4. You are given point P whose coordinates are 1, 1, 1 meter. So all the coordinates x, y and z are 1 meter each. Just put the values, minus 4, x is 1 meter, y is 1 meter, plus 4, z is 1 meter. Okay. Now simplify. This is 1 raised to 4 means 1 only, 1 into 4 is 4. This is minus 4 into 1 that is minus 4. Altogether minus 4 plus 4 will come out to be 0, correct. So in this case, x component of electric field has come out to be 0. Similarly, let us find out y component of electric field. Come on, by similar formula, can you say minus del V by del y, minus del V by del y, correct. That is minus del by del y of V, and V formula is same formula written here, which is given to you in the statement. Okay. Mind well, now we are taking derivative, partial derivative with respect to y. So x and z are to be treated as constants. Come on, minus 2x square is constant. Derivative of y with respect to y is 1. Minus plus minus 3z is to be taken as constant, and derivative of y cube with respect to y, derivative of y cube with respect to y, it is 3y square. Power you should write as a multiplier into y raised to 3 minus 1 that is 2, correct. Then minus minus plus, but because we are taking partial derivative with respect to y, right now x and z are to be treated as constant. So this is altogether a single constant term whose derivative will be 0, correct. Now just place the x and y coordinate, but before that you just simplify. Minus 2x square as it is, come on, minus as it is, 3 3s are 9, y square z. Put up the coordinates, come on, minus 2 into 1 square minus 9 into y value is 1, z value is also 1. Simplify. This is minus 2 minus 9, that is minus 11, correct. What about Z component of electric field? It is minus del V by del Z. That is minus del by del Z of V. Same formula of V I have written over here, no change. And now you are taking partial derivative with respect to Z. So X and Y are to be treated as constants. Come on, minus as it is. Because X and Y are to be treated as constant, this is altogether a single constant term whose derivative will be 0. Minus plus minus 3y cube is to be taken as constant right now, and derivative of Z with respect to Z is 1, minus minus plus 4 into x to be taken as constant, and derivative of Z raised to 4 with respect to Z will be 4 into Z cube, 4 into Z cube. Power will become multiplier into Z raised to 4 minus 1, that is 3, correct? Simplify. This is minus 3y cube plus 4 4s are 16 x into Z cube. Put up the coordinates. Come on, y coordinate is 1 meter, x coordinate is also 1 meter, z coordinate is also 1 meter, correct? Simplify. This is minus 3, this is plus 16, minus 3 plus 16, that is plus 13, plus 13. Simple. We know x component of electric field, we know y component also, we know z component also. Now, don't you know the representation of a vector in 3 dimensions? For electric field vector, you can write vector E equals to, as you studied in 11th standard, Exi hat plus Eyj hat plus Ezk hat, correct? Come on. What is Ex value right now? Ex value is 0. Ex value is 0. What about Ey? Ey has come out to be minus 11. Ey is minus 11. And what about Ez? Ez has come out to be plus 13 into k hat. So altogether it is minus 11 j hat plus 13 k hat, correct? This is the vectorial form of electric field in the present case, which is the final answer, okay? Now read the statement of exercise numerical number 4. Read it? Look. We have one charged small droplet, okay, on the surfaces of which, come on, potentially suppose V small r. The small r you must write well below V, okay. It is the potential on the surface of that charged drop whose radius is small r. Suppose the charge is small q, then you know by formula k into charge upon radius, k into charge upon radius, correct? This potential they have given on the surface of small droplet, they have given 500 volt. What about small k value? Everybody must have remembered that was the proportionality constant coming in Coulomb's law, 9 into 10 raised to 9, come on, Newton meter square upon Coulomb square, fine. What about small q? Charge on the surface of that small droplet which is given to you 3 into 10 raised to minus 10 Coulomb. If they give in microcoulomb or nanocoulomb or picocoulomb, you must convert into coulomb. Have you remembered? Microcoulomb to coulomb, multiply by 10 raised to minus 6. Nanocoulomb to coulomb, multiply by 10 raised to minus 9. And picocoulomb to coulomb, you must multiply by 10 raised to minus 12. Simple. Right now they have given this charge in coulomb only, so no problem. This radius as it is. Now find out that radius. By simplification you get 5.4 into 10 raised to minus 3, that many meter. Leave it in meter only. Now what have they given in the statement? Such 8 identical charged droplets merge into each other and it forms one big drop, okay? If that big drop has radius capital R, then don't you know, in such a process of association, total volume will remain constant. That is, whatever was the total initial volume, same will be total final volume. What was the total initial volume? For one droplet, it was 4 upon 3 pi r cube, correct? Here small r. And such 8 small identical droplets are combining, so I must multiply by 8 in order to find out total initial volume, and that should be equal to final volume. Finally, you have only one big drop whose radius, if I am taking capital R, then its volume would be 4 upon 3 pi capital R cube. Simplify. 4 upon 3 pi getting cancel. Cube root of 8 is 2, cube root of small r cube is small r, cube root of capital R cube is capital R, correct? Find out capital R from here, 2 into small r, 2 into small r value is right now 5.4 into 10 raised to minus 3. Simplify, it is now 10.8 multiplied by 10 raised to minus 3, that many meter, correct? And now they have asked the potential on the surface of big drop, let it be V capital R. Again by formula it is K into charge divided by radius. K into charge on the surface of big drop I am taking capital Q divided by radius of big drop I am taking capital R. This small k as it is. What about capital Q? It is the total charge on the surface of big drop, but according to law of conservation of electric charge, you know total charge should remain constant. Whatever was the total charge on the surface of all the 8 identical small droplets, same must be the charge on the surface of big one spherical drop. Then capital Q should be equal to small q plus small q. How many times? 8 times. That is 8 into small q. Capital Q is 8 into small q. 8 into small q. My dears, this is not 89. This is not 89. This is 8 into small q. 8 into small q. Got it? Upon capital R. Now small k is 9 into 10 raised to 9 Newton meter square upon Coulomb square. What about this small q value? Small q is given to you 3 into 10 raised to minus 10 Coulomb. Small q is 3 into 10 raised to minus 10 Coulomb. This 8 as it is. What about capital R? Capital R is 10.8 into 10 raised to minus 3, that many meter. Capital R is 10.8 into 10 raised to minus 3 meter, correct? Simplify, answer is 2000 volt. 2000 volt. Leave proper gap, write capital V symbol for volt and don't put any full stop. Got it? Fine. Read now statement for number 5. Read it? Look. Here we have to solve the sum in 3 different ways. That is what they have stated in the statement. But I have found out 4th method also. In all totally there are only 4 methods. Okay? We will see all these 4 methods one by one. In each method we will obtain same final result. Okay? Now what is that result? What is it about? I am showing you. If you have a sphere of radius capital R suppose, and you want to deposit total capital Q amount of electric charge on its surface, then in that process how much total work do you need to do, or how much total electrostatic potential energy will be stored in the electric field surrounding to its surface because of the charge deposited on the surface. Either of these two we have to find out. Either you find out amount of work done or you find out amount of electrostatic potential energy, it is one and same. Okay? Let us find out this result in 4 different methods. First method is about finding average electric potential. I am showing you. When you begin the charging of the sphere, say at time t equal to 0, actually at the very first moment there is no charge on the surface of the sphere. No charge, then no potential. So initial potential I am taking 0, correct? After t time, suppose you have deposited totally capital Q amount of charge on the surface, then because of that it achieves some potential given by formula in words, you know, K into charge upon radius. K into charge upon radius. K into charge is capital Q divided by radius is capital R, correct? Now here it so happens that K upon R, this ratio remains constant. As you go on increasing the value of Q, the value of electric potential on the surface will go on increasing proportionately. And whenever there is a proportionality relation, you can always go for finding average value this way, initial value plus final value divided by 2. Initial potential was V1, final potential was V2, summation of two values divided by 2, summation of two values divided by 2. This way you can find out average value when there is direct proportionality relation between two given quantities, correct? Fine. Now average potential in this case we can find out this way, initial potential plus final potential divided by 2, summation of two values divided by 2, this plus this upon 2, that is this plus this upon 2, when you take this plus this it is kq upon r divided by 2, so it is finally kq upon 2r, kq upon 2r, correct? And now what is the formula of electrostatic potential energy? It is actually constant potential multiplied by charge, constant potential multiplied by charge. But here potential does not remain constant during the process of charging, it goes on increasing linearly, proportionately, and that is why we go for using here average value, correct? So in this case you should remember the formula, average value of the potential during the process of charging multiplied by total final charge deposited on the surface of the sphere. So average potential multiplied by charge, average potential multiplied by charge. What is average potential? It is kq upon 2r, kq upon 2r multiplied by total final charge, that is capital Q. Now it is k into q, that is q square upon 2r, kq square upon 2r, kq square upon 2r, correct? So this is the amount of electrostatic potential energy stored in the electric field in a region near the surface of a charged sphere, correct? Fine. How can you say that electric field has some electrostatic potential energy? I am showing you. If the charged sphere is this, correct, then because of deposition of positive charges, it must have its electric field radially outward. That is what I am showing by symbol of blue colored arrows. I mean they show electric field lines, okay, radially outward. Now this electric field has got some capacity of doing work. How? Simple. Just put any charge, might be positive, might be negative. If you place here positive charge, it will be getting repelled, correct? And if you place negative charge, it will be attracted. So what I mean to say, if you place any charge in this electric field, then electric force is definitely exerted. There is a displacement also in the direction of force. Then you know force multiplied by displacement in the direction of force will give you amount of work done. So I mean to say this electric field has got some capacity of doing work. And you know if any system in any configuration has got some capacity of doing work, it is said to be having some potential energy. That is why we say that this electric field has got some electrostatic potential energy. In this case, by formula, we have found out it is this much, k into square of charge divided by double the value of radius. Simple? Fine. Now let us go for second method. You know, charged sphere can be taken as a capacitor. Charged sphere can be taken as a capacitor. And in case of capacitor, don't you know, electrostatic potential energy is given by this formula 1 by 2 QV, 1 by 2 QV. Now 1 by 2 as it is, Q as it is. What about V? It is the potential on the surface of a charged sphere given by formula K into charge upon radius, K into charge upon radius, correct? Now tell me 1 by 2 as it is, K as it is, Q into Q, that is Q square upon R as it is. In short, K Q square upon 2R, K Q square upon 2R, correct? We are getting same formula, okay? Method is different, but formula every time we will be getting same. Third method, that is the method of integration. I am showing you. When you are just undergoing that process of charging at a particular stage on the surface of a charged sphere, suppose amount of electric charge is small q, and because of small q amount of electric charge on the surface, it has some potential given by V equals to K into charge upon radius, correct? Now what we do, we just additionally put extra amount of electric charge, but very small, infinitesimally small, differentially small, say dq. When you will use the symbol dq, provided limit delta q tends to 0, correct? So that amount of electric charge deposited later on, it is dq, it is that small, though we deposit that charge, the potential on the surface remains almost same, correct? And that constant potential we are taking capital V. I repeat, after q amount of charge, when you put another dq amount of charge additionally, then the potential remains almost constant, correct? And because that charge is very small, we are showing it by symbol dq. Then because the charge is increasing by slight amount, here electrostatic potential energy will also increase by slight amount. So I am putting the symbol du. Potential energy is potential multiplied by charge. Here it is not charge, it is increase in the value of charge. So I am putting here increase in the value of electrostatic potential energy, shown by symbol du, correct? Fine. Now this V is k into charge upon radius, this dq as it is. Now just go for taking integration from between the initial moment and final moment on both the sides. Come on, here integration 1 du, integration 1 du. Because the variable is in terms of electrostatic potential energy, the limits also must be specified in terms of electrostatic potential energy. Initially, when you begin that process of charging, the sphere had no charge, no electric field, no storage of electrostatic potential energy. So initial value of that energy is 0. And finally, let it be capital U. Here k upon r can be taken constant, and out of the symbol of integration, integration q dq, integration q dq. Here variable is in terms of charge, so I must specify limits in terms of charge. Initially charge on the surface of sphere was 0, finally let it be capital Q. Integration 1 du is nothing but u from 0 to u, from 0 to u. K upon r as it is. What is integration q dq? It is q square by 2, q square by 2. You know integration x dx is nothing but x square by 2. Similarly, integration q dq will be q square by 2, but from where to where? From 0 to capital Q, from 0 to capital Q, correct? Now in place of u, you must write upper limit, that is u. After putting minus sign in place of u, you must write lower limit, that is 0. Here k upon r as it is, instead of small q, you may write capital Q, q square by 2. After putting minus sign, instead of small q, when you write 0, 0 upon 2 will be 0. Come on, u minus 0, that is u, and this is kq square upon 2r, kq square upon 2r, correct? Still we are getting same result, okay? And now last method. Believe me, there are only 4 methods, okay? There is no 5th method. 4th method is this, that is known as graphical method. See, as you are increasing the charge on the surface of the sphere, gradually more and more, then the potential is increasing proportionately. And that's why the graph of electric potential versus charge comes out to be a straight line, because the relation of between V dash and Q is of direct proportionality relation, that's why. Come on, we are getting straight line graph, and when charge is 0, potential is also 0. When x coordinate is 0, y coordinate is also 0, then that straight line must be passing through origin, okay? Now, at this final point on the graph, you must have deposited capital Q amount of charge on the surface, and then the maximum potential, right now potential is taken on y axis, so this vertical distance will give me y coordinate, that is potential. And when charge Q is there on the surface, what is the potential? K into charge upon radius, K into charge upon radius, correct? Come on, this is the vertical distance, and what about the horizontal distance? It will give you x coordinate, and that much potential the surface has when there is a charge capital Q on the surface, correct? So this much will give you maximum charge on that surface, let it be capital Q. When charge is capital Q, at that time this is the potential, which is K into charge upon radius, correct? Now tell me, because we are getting here straight line graph, what is the area under that straight line graph? It will be area of this part OAB. But shape wise, how do you find it? Triangle. So this is nothing but area of a triangle OAB. So in this case, the amount of electrostatic potential energy stored in the electric field surrounding to charged sphere can be found out by finding area enclosed under the graph of potential versus charge, that is area of triangular part OAB. I have written here, capital U is right now area of triangle OAB. Now remember, in 11th standard also you have found out the amount of work done or amount of energy in the similar way in two different cases. Remembered, in thermodynamics you are plotting graph of pressure versus volume. At that time you are finding area enclosed under the graph, and that area was giving you amount of work done. And similarly, you are plotting the graph of F versus X in case of a variable force. How much amount of work is done, that you are finding by finding area enclosed under the graph of F versus X, correct? Similarly here, by finding area enclosed under the graph of potential versus charge, we can find out amount of work done or amount of energy stored in the process of charging. Come on, it is area of a triangle. Don't you know area of a triangle in words? 1 by 2 into, come on, base into height. 1 by 2 into base into height. 1 by 2 into base into height. Base is this much, OB, correct? I am writing here OB. Multiply by height. Height is this much, AB. That height I am writing, okay? Now 1 by 2 as it is, OB is this much, which is capital Q, correct? And multiply by AB. This AB is value of electric potential, and it is KQ upon R. KQ upon R. Come on, 1 by 2, K, Q into Q, that is Q square upon R. Altogether is KQ square upon 2R. KQ square upon 2R. Okay. Please remember this result, because sometimes they may give you direct values of Q and R. You may put it here, you may find out the answer very urgently if you have remembered this formula. Okay. KQ square upon 2R. Now read the statement of example number 6. Read it. Look. We have uniformly charged hemisphere, correct? And we are asked to find out the total electric potential at this centroid. At the centroid. Now that centroid I am showing by symbol C, and potential at center I am showing by symbol Vc, correct? This potential here we will find out by very easy method, the shortest method. And what is that? I am showing you. In this case, whatever is the potential on the surface, same is the potential at this center. And what is the potential on the surface? That you know very well by formula, K into charge upon radius. K into charge upon radius. K into charge upon radius. But mind well, this charge you must consider only that amount of total charge which is deposited on this hemispherical surface, not on the complete spherical surface, because which is the object given to us? Complete sphere? No, hemisphere. So this is charge which is deposited on hemispherical surface. Remember, in case of uniform surface charge distribution, how will you find out total amount of electric charge? By formula. Remember in words, surface charge density multiplied by surface area. Surface charge density I am taking sigma, surface area I am taking capital A. This 1 upon R I am writing as it is. What about small k? By formula 1 upon 4 pi epsilon 0, sigma as it is. What about A? Surface area of given object, right now it is hemisphere. So it will have area half of area of sphere. What is area of sphere? 4 pi r square, half of that. So I am writing here 2 pi r square. Take care. Now simplify. Pi will cancel. 2 2s are 4, so there will be 2 in the denominator. Then 1 r will be getting cancelled from here and here. So left is 1 r in the numerator. So r into sigma. r into sigma upon 2 epsilon 0, r into sigma upon 2 epsilon 0, r into sigma upon 2 epsilon 0. Correct? Fine. Read now statement of number 7. Read it? Look. First of all, try to understand this figure. What is given to us? 3 concentric charged spherical shells, A, B and C. Smallest is A, bigger than that is B, still bigger than that is C. Okay? So, smallest is A, biggest is C. The surface charge densities on these 3 spheres respectively are sigma, minus sigma and sigma. Now we are asked to find out total electric potential on the surface of spherical shell capital A, suppose at this very point. Let us find out. Now tell me, what is the potential on the surface of a charged sphere? K into charge upon radius, correct? K upon R as it is. In case of uniform surface charge distribution of electric charges, what is total electric charge? It is surface charge density multiplied by surface area. Fine. Now this 1 upon R I am writing as it is. What is small k? 1 upon 4 pi epsilon 0. Sigma as it is. What about capital A? It will be surface area of complete sphere, which is 4 pi R square. Right? Because we are given spherical shell. Okay. Come on, this surface area will be 4 pi R square. Simplify. 4 pi will cancel. R square upon R. So, there is 1 R in the numerator and sigma upon epsilon 0. Sigma upon epsilon 0. Better in this case you remember in words, the formula of potential on the surface is sigma upon epsilon 0 into R, that is surface charge density divided by epsilon 0 multiplied by radius of given spherical shell. Correct? Fine. Now, according to this formula, just tell me what will be potential on the surface of charged spherical shell capital A, just due to its own charge, let it be VA, because the radius of spherical shell A is small a, right? So, I am putting symbol VA. This is due to charge only on A. Come on, according to this formula, it is sigma upon epsilon 0 into radius. Sigma upon epsilon 0 into radius. Radius is small a. Correct? Fine. What about potential on the surface of spherical shell capital B? Because of only its own charge, let it be V small b. Then it is according to this formula, surface charge density divided by epsilon 0. Surface charge density, here it is minus sigma. So, instead of sigma, I must write minus sigma upon epsilon 0 into radius of spherical shell capital B, which is small b. This radius is, you can see, small b, correct? And what about potential on the surface of spherical shell C? Because only because of its own charge, let it be Vc, correct? It is according to this formula, surface charge density, which is sigma upon epsilon 0 multiplied by radius of cell C, it is small c. Radius of capital C is this much, which is small c, correct? Mind well, these are the potentials on the surfaces of respective cells because of only those charges which are on their surfaces. Okay. So, this much potentials these spherical cells would have on their surfaces if only one spherical cell at a time you are considering. Okay. Then, now, if the whole system is present like this, then what is the total potential on the surface of cell A? Let it be VA, correct? Then it will be addition of 3 potential values, because I told you as many charges, that many values of electric potential. You have 3 charges on the surfaces of A, B and C. That's why I need to make addition of 3 potential values. Okay, VA plus VB plus VC. Now tell me, VA plus VB plus VC, that you can find out from here directly, correct? VA plus VB plus VC, that is this plus this plus this. Come on, sigma upon epsilon 0, sigma upon epsilon 0, sigma upon epsilon 0 can be taken common. Inside the bracket, A minus B plus C. Here it is, A minus B plus C. Now you may surprise that why we are making addition straight away, correct? Because we are asked to find out total potential on the surface of innermost charged cell. Innermost charged cell is cell A. Look, here you will have potential due to 3 charges. First this charge, second this one, third this one, correct? Potential on the surface of charged spherical cell A, because of its own charge, will be same as this, because it is potential on the surface due to its own charge. Come on, sigma upon epsilon 0 into small a, correct? But same point is inside this cell B, correct? Fine. For any point inside the charged cell, the potential is as good as or equal to potential on the surface, and potential on the surface is this much, correct? Similarly, the same point is also inside the third biggermost cell, that is cell C, and potential at any point inside the charged spherical cell is equal to potential on its surface, and so far potential on the surface of spherical cell C is concerned, it is this much, correct? So at this very point, because of all the 3 amounts of electric charges on the respective cells, what will be total potential? It will be this plus this plus this. So VA plus VB plus VC. VA plus VB plus VC, in the addition of these 3 terms, you can take sigma upon epsilon 0 common, then left inside the bracket is, come on, A minus B plus C. A minus B plus C. Got it? This is the easiest one, but they may make this sum little bit difficult. They may ask you to find out total potential on the surface of cell B, or they may ask total potential on the surface of cell C also, they may ask. So let us find out those potentials also. Look, extra sum we take. If at all they ask total potential on the surface of spherical cell B, let it be VB, okay? Then you change the symbol of this potential. Instead of VA, you must write VA dash. These 2 potentials, you may keep them as it is, because see, you are taking now point here, correct? Now this point is outside this charged spherical cell, and for any point outside the charged spherical cell, what is the potential? K into charge upon distance, K into charge upon distance. So that potential is different than this, so I am putting VA dash. Come on, this is the potential at this very point because of this charge, and you can see this point is outside the cell A. For a point outside the charged spherical cell, what is the potential inverse? K into charge upon distance, K into charge on this cell A divided by distance of this point from this common center, it is small b. What about charge? Charge is given by formula surface charge density multiplied by surface area. Here surface charge density is sigma multiplied by surface area of a sphere with radius a, it is 4 pi a square, correct? VB and VC values as it is, because come on, this point is on the surface of charged spherical cell B, and for a point on the surface of charged spherical cell, the potential is, come on, minus sigma upon epsilon 0 into B, I mean equal to VB. So I am writing same symbol here also, VC. Now for same point, you can see it is inside this cell, and for any point inside the charged spherical cell, potential is just equal to potential on the surface, and potential on the surface was earlier also VC, here also VC, correct? So these 2 potentials are still same, so I am putting same symbol, but this potential is changing, so I am instead of V I am putting VA dash. Come on. VA dash as I explained is this much. What about VB? VB is minus sigma upon epsilon 0 into B, minus sigma upon epsilon 0 into B. VC is sigma upon epsilon 0 into C, sigma upon epsilon 0 into C, correct? Now just simplify carefully. K is 1 upon 4 pi epsilon 0, sigma into 4 pi a square as it is, B as it is, these two terms also as it is. Now what part you can take common? Sigma upon epsilon 0, sigma upon epsilon 0, sigma upon epsilon 0 you can take common. 4 pi will cancel. Left inside the bracket from here is a square upon B minus B plus C, because sigma upon epsilon 0 we have taken out. Okay. So this must be the total potential on the surface of cell B, correct? Similarly, they may ask potential on the surface of cell C. Let us find out that potential. Still you need to make change here also. Instead of VA dash, now you must write VA double dash. Instead of VB, you must write VB dash. VC you can keep as it is. How I am showing you. Now you are taking point over here, correct? Now tell me, this point is located outside the cell A, and so potential will be K into charge upon distance. Earlier distance was this much, correct? But now distance is this much. So because of this change in this distance, I am just changing the value, sign of the potential. Instead of VA dash, I am putting VA double dash, correct? Because there is a change in this distance, I must change the symbol. Instead of VA dash, I am putting VA double dash. Come on, what about VB? Earlier you were taking this point, correct? Now you are taking this point. Now this point is outside this cell B, correct? Then you should consider this much distance, which is not B, it is small c now. So instead of B, now the distance is to be changed. Because distance is changing, this potential will change. Instead of VB, you must write VB dash, correct? And VC you can keep as it is, because this point you are taking on the surface of cell C, correct? And for this point, because it is on the surface, for cell C it is on the surface, the potential will be K into charge upon radius. It will remain constant, same. So VC is remaining same throughout, correct? Here it was VB, here it is VB, but now it is VB dash. Here it was VA, here it is VA dash, here it is VA double dash, correct? Why? I repeat, earlier you were taking this point, correct? Then this much was the distance from the center. Then after you had taken this point, then this is the distance. Then after you are taking this point, so this is the distance. And because of the change in distance, the potential at these points, because of this charge, because there is a change in distance, naturally the potential value will change. So we must change the sign. Here is VA, here is VA dash, here is VA double dash, correct? Come on, now let us find out. What is this VA double dash? It is potential at this very point because of the charge on cell A. Because this point is outside the cell, come on, K into charge upon distance, K into charge. Charge on the spherical cell A is surface charge density multiplied by surface area of cell A, which is 4 pi into A square, divided by distance of this point from this common center, it is small c. So I am putting small c here, correct? Come on, what about VB dash? It is potential at the same point, but due to this charge, correct? Come on, again it is K into charge upon distance, K into charge. Charge is, come on, surface charge density multiplied by surface area. For cell B, what is surface charge density? Minus sigma. So I am writing minus sigma. Multiplied by surface area of this cell. For a cell having radius small b, what is surface area? 4 pi b square. Divided by distance of this point from this common center, it is this much, which is c only. So I am writing c. Plus VC. Come on. This point is on the surface of third cell, and for a point taken on the surface of the charge cell, what is the original formula? K into charge upon radius. K into charge upon radius. And based upon this same formula, K into charge upon radius, we got this formula. Sigma upon epsilon 0 into radius of given sphere. Come on. Sigma upon epsilon 0 into radius of given sphere is c. Correct? I repeat. Why VC is same? Because here also we had used VC, here also VC, here also VC, correct? Everywhere it indicates the potential on the surface of third cell C because of its own charge, and it is a point on the surface of a charged cell. Then what is potential formula? K into charge upon radius. And based upon the same formula, K into charge upon radius, we got this formula, sigma upon epsilon 0 into radius, correct? But now sigma upon epsilon 0 as it is, but what about radius? Radius of third cell is C, small c, correct? And the surface charge density was also sigma, so I had written here sigma. Had there been minus sigma suppose, then you should write here minus sigma, got it? Fine. Now what is K? K is 1 upon 4 pi epsilon 0, sigma into 4 pi square upon C as it is, plus minus minus, K is 1 upon 4 pi epsilon 0, sigma into 4 pi b square upon C as it is, this term also as it is. Simplify, 4 pi will cancel, sigma upon epsilon 0 I am taking common, left inside the bracket from here is a square upon C, correct? Come on, 4 pi getting cancelled, then sigma upon epsilon 0 already I have taken out, left inside the bracket from here is minus b square upon C, minus b square upon C, and sigma upon epsilon 0 we have taken out, so left inside the bracket is C, correct? So they may ask you to find out total potential on the surface of third biggest spherical shell, that is cell C, okay, fine. They may change the order, here innermost or the smallest cell is A and biggest cell is C. They may change the order, they may write here A, then here B and here also C, correct? So take care, you should remember formula as far as possible in words, okay.